I wanted to create a household system for reuse of grey water in the garden, so I took into consideration all the problems I might encounter. It needs to fit in the average laundry room, be built out of materials I had access to, be easily maintainable, and supply usable water, as well as being simple enough for families to use easily. So I got to work researching how I'd accomplish that. I started off by researching the topic of grey water reuse. The most important piece of information I found was that what you can legally use grey water from and for varies depending on your jurisdiction. Here in Ontario, however, there aren't any specific regulations. Through my research, I found that washing machines were the most consistently legal source of grey water. And with that in mind, I did some more research on the topic and then started sketching. I wanted to design two parts of the system. One would be a panel that would allow the user to control whether their grey water was flowing into their reuse system or into the sewer to meet that accessibility problem. I originally designed it with a switch, but was concerned that it may be confused with a light switch, so I redesigned it with a button instead. The second part of the system was a filter. Many detergents are high in sodium and phosphate, which can be harmful to plants in high amounts, so I designed a sand filter that would separate the salty, phosphate-filled detergent from the water. My first design relied on gravity to push the water through the system, but would be hard to clean. My second sketch was based on pressure instead of gravity, which would make it easier to clean, but still problematic when trying to get the wet filter material out of these small holes. I then started designing with a different cleaning method in mind, backwashing. Instead of completely removing all of the filter material, clean water would be sent backwards through the system to remove the pollutants caught in the system. Finally, I removed the barriers between materials as I deemed them unnecessary and added mesh over the water ins and outs to prevent pipes being clogged by the materials. After a trip to the hardware store, it was time to start building the first prototype. The first problem I encountered was the three-way valve. I couldn't find a simple one with one handle, so I had to use this one with two. I redesigned my original idea for how I was going to control water flow between the system and sewer. First, I tried using a belt which I had from an old Lego set to turn the knobs, which didn't work as the belt didn't quite fit. So I took off the knobs, 3D printed gears to fit the knobs, and reattached them to the pipe, and it worked great. This motor just didn't have enough torque. We're going to try it with this motor and see how that turns out. The other motor, however, also just could not get enough torque even out of a 9-volt battery. I have a new idea. What if we just get rid of the Arduino completely and just create a crank with the belt and the gears to turn each valve together, but manually? I 3D modeled and printed the pieces I would need for this. It looked promising, but I didn't quite have the tension I needed. So I extended the distance between the gears and voila! It's able to turn the gears, and you can see how if I had a motor that did have enough torque in this place, it would be able to work. Now that the valve system was done, it was time to start building the first prototype of the filter. The construction of the first prototype was fairly simple. I put it together based on the fourth sketch design, filled it with sand and gravel, and ran some water through it. It worked! Water was passing through the filter, but I was worried that it took too long for it to get from end to end. So after rebuilding and a few messes, I had a shorter filter. The shorter filter took a much more reasonable time to filter water through, and being the size, it was much more reasonable to mount vertically, potentially taking up even less space in the laundry. Okay, we're gonna try a salt level test. So the detergent water before filter gave us a reading of 4, which accounts for 1,270 parts per million of salt. Now let's filter it and see what comes out. So we just tested the second filter. It gave us a reading of 2.8, which corresponds to 720 parts per million. The button was fairly simple to make. I soldered together the components, and without a motor, it's a proof of concept and it can turn the light on and off. In conclusion, I think the system works well. The filter is able to remove harmful chemicals that can damage the plants families are trying to grow. It is easy to use by simply pressing a button to turn it on and off, and it doesn't take up any unneeded space. There are still a couple of things I would change though. Firstly, the prototype was made out of PVC as it was the most accessible material to me, but in general is a horrible material for the environment. The commercial product would ideally be made out of steel. Also, the pipe system would benefit from actually having a motor to turn the gears. Unfortunately, I don't have the resources to make that a reality at the moment. I think this was a successful design. Easy, functional, and adaptable. That's all. Thanks for watching.